I'm Margarette
And I'm Hinson, and for the past 4 weeks we have been working on a project with the rockets. Our research topic is to design the optimal rocket. And by optimal rocket we mean the rocket that has the best combination of nose cones and fins. Before we go into more depth, Margaret's going to tell you a little bit about the history of the rocket.
The first rocket was made in China, and it was actually a gunpowder engine rocket, and it was made by accident. They used short bamboo sticks and filled them with gunpowder, and they would throw that into a pit of fire, and they would use that as fireworks. But one time it misfired and it shot the bamboo stick up in the air, and a man saw this happen and decided to attach a long bamboo stick to that rocket, and he used it for battles, and they called them fire arrows. So now we're going to get into like the basics of flight science. There are 4 forces of flight. There's drag and thrust, gravity and lift. Drag and thrust oppose each other, and as you can see in this picture here, thrust is a force that tries to move you forward, and drag is what tries to stop you or pull you back. And the force of lift is what elevates you, and gravity is what tries to bring you down.
The two variables we manipulated in this for this research were the nose cones and the fins. Both the nose cones and the fins affect the drag coefficient, as drag is what Margaret explained. But the nose cones greatly impact the aerodynamics of the rocket because it's the first thing that the air hits as the rocket's going through the air. The fins are used more for stability, and it controls the direction of the rocket. The importance of this research is that it could be used by model rocket companies to create a better rocket, one that can go higher, and it could be used on a larger scale for like missiles and spacecrafts, but the first one's more likely.
And this picture right here shows a diagram of what our rocket looked like, but instead of using a parachute recovery system, we used a streamer, and it was a tumble recovery system. And we'll explain that more in detail later.
One requirement of a research paper with the literature review. The literature review is whenever you go and research that has already been done on your topic. We had trouble finding research on the combination of nose cones and fins. We could only find either research on different nose cones or different fins. The first research article we found was on nose cones. It was by three researchers, and they were trying to find the best nose cone for their rocket target system. The thing is, they didn't make like physical rockets. They made model rockets on SolidWorks. It's software that you can build stuff on, and they exported it to a wind tunnel simulator, and they calculated the drag of the rocket. They found out that the elliptical nose cone performed the best. It had the lowest amount of drag, and the conical nose cone it performed the worst because it had the highest coefficient of drag.
And you can see all that information right here on this graph. After we did research on the nose cones, we then moved on to the fins, and we found 2 sources. One was by Apogee Components, and Apogee Components is a company that specializes in model rockets, and they were looking for the perfect fins, and they tested these 4 types of fins right here, and they concluded that the elliptical fin and the tapered swept fin performed the worst, and the parallelogram and the rectangular fin performed the best. But that contradicted our results because in ours the tapered swept fin actually performed the best. The other source that we looked at was by Joseph R. Sims III, and he was looking at the fin geometry and how the mass of the fin, the shape of the fin, and the width of the fin greatly impacts the stability and the control you have on a rocket.
The next section was the methodology section. We made 3 different rockets. Each had a different type of fin on it. The body was made out of a cardboard tube, and the fins were made out of balsa wood. The measurements of the fin were calculated according to these equations, and the three different types of fins we had were the clip delta, the elliptical, and the tapered swept. We made four nose cones. We had 5 in total. The 4 nose cones that we made were made out of blocks of balsa wood. We had 5 different types of nose cones. Sure, I'll show them up there. That was the parabolic, the cone, the hemispherical, the ogive, and the elliptical. The elliptical one is the one that was pre-made. It was made out of plastic. And down at the bottom we have the different types of fins, the elliptical, the clip delta, and the tapered swept. This chart right here is the different combinations of rockets that we tested. We had 15 in total. So yeah. Each rocket used an A3 engine, which is proportional to the size of the rocket. We attached an 18-inch by 1.8-inch streamer to the rocket to create a tumble recovery system, so we could reuse the rockets. The streamers were made in a 10-to-1 ratio because researchers have found that is the best proportion to make a safe recovery for a model rocket.
After we built all the rockets, we did testing in a wind tunnel first. We did this so that if the rockets got damaged during launches, it wouldn't skew our data. And what we tested for was the drag coefficient, which is this. We used this equation right here on the right. We were given the one on the left, and we had to rearrange it to this equation here. And after we got our data from the wind tunnel, we used a software called Logger Pro. And what we did was inputted the velocity, as you can see here, right there on the left, and then the force on the right. And we had to do this 14 more times because we have to do it individually for the different combinations. And here's all the coefficient of drags for each combination. As you can see, the tapered swept with the elliptical had the lowest coefficient of drag, and the highest ones we had were the elliptical fin with the cone and the ogive nose cones. One of the other variables we looked at was theoretical height, and this is the formula that we used. You see all that there. One of the reasons that we used right there, that equation, the mass initial minus the time increment times the change in mass, was because we knew that as time went on, your engine would burn fuel, so it would decrease your mass as the time went on. So we had to input that for the formula. And this is the charts for the different theoretical heights. As you can see in this top one here, the elliptical with the elliptical performed the best, and down here, the elliptical with the tapered swept performed the best, but here, the parabolic with the clip delta performed the best. After we did testing in the wind tunnels, we tested them out in the fields and rocket launches. What we calculated for was the time until apogee, which is the maximum altitude that your rocket can reach, and the time it took for the rocket to launch and land back down. And then we used these here, the altimeters, to calculate the angles of the rockets. And we used those angles to calculate for the estimated altitude. And this diagram here shows what the field looked like. We had 3 different people set up 20 meters from the launch pad and 120 degrees around. And this equation here was used to calculate the estimated altitude. Your rocket would be up here when it launches. This would be the 20 meters, and the person standing was here.
To summarize what we tested for the drag coefficient, the theoretical height, the estimated altitude, and we timed for the time until apogee. Apogee is the highest the rocket will go before it starts falling back down to the ground. And we also timed the time it took till it hit the ground again. This is the chart for all the information that we calculated or gathered for the 15 launches. You see we have the combinations, the time it was in the air for, the time until apogee, the angle by using the altimeters, the estimated altitude, and the theoretical height reached. Thing to note is that the rocket combination with the highest theoretical height did not necessarily have the highest estimated height. As you can see for the tapered swept elliptical, it had a 50.4 meter theoretical height, but it only reached 47.1. As with every experiment, you will have complications. We had one giant complication. We call it the crash and burn of our 13th combination, as you can see here. This was the ogive and clip delta combination. What we think happened was it went up normal, but around here, the engine is supposed to stay in place with a tube, but the tube is glued to the inside of the rocket. We think that the glue came loose and it slid up here as it was going up, and the change in mass caused the rocket to flip around, and what happened was it came back down towards the ground with the engine still going on, so it basically made full impact with the ground, and this is what happened.
We also had some disasters or minor complications. One of them was the shearing of the fins, which you got a picture right there. That is when the grain of the wood of your fin is not perpendicular to your rocket's flight. So if your rocket is going upwards and the grain of the wood of the fin is also going upwards, it makes the fin easily breakable. We also had igniter failures. We used a car battery. It would short that to launch and ignite the engine, but on some of the rockets, the engine would not light. We also had fins, streamers, and tube burning. As you saw in the crash and burn rocket, the end of the rocket and the end of the tube and the end of the fins would burn. And sometimes if you had the streamer too close to your engine, it would melt the plastic bag. We also had damaged nose cones and fins. That would happen when the rocket's coming down, and if it lands too hard, you got it.
You also have to take into account errors and inaccuracies. Some of these include experimental errors. We may have stopped the stopwatches too early or too late, and we may have used the altimeters wrong. So as you can see here, altimeters are plastic gun-looking things where you hold a trigger and aim at the rocket to get the angle. And this little plastic sliding thing goes and calculates the angle for you. Well, if you bring it down too fast, the sliding thing will reset and go back up to the top, and you won't get the angle of the rocket. Some other errors include errors in construction. We're not perfect. We could not make these rockets perfect. The fins may have been misaligned. They may have been crooked. Then we made the nose cones by ourselves with for the exception of one, the elliptical nose cone. As you can see here, this is the nose cone. This is the conical nose cone that we made, and the next one is the pre-made, perfect conical nose cone. Some other factors you have to include is the environmental factors such as the wind, the air pressure, other things that the environment tries to throw at you, and you just have to deal with it. Another one would be the rocket engine inconsistencies. Not all the engines do the same thing. They might quit early, they might not go off at all.
So after we analyzed all our data and got our results, we concluded that the tapered swept fin with the elliptical nose cone performed the best, And we say this because it had the lowest coefficient of drag, it reached the highest theoretical altitude, and it had the fastest velocity. But you do still have to account for the confounding variables, which are factors that you cannot eliminate or control from the experiment. And those would be the misalignment of the fins, the asymmetrical nose cones, and like wind variables.
If we were to take this research on, if we were to continue this research in the future, things we could change would be the testing, what we used to test the rockets. We might not use the stopwatches on our phones. We would use something better. We probably wouldn't use the plastic altimeters and use something more accurate. We would also increase the scale of the rocket, increase the scale of the project. We would probably not use just a foot tube rocket. We would probably use two-stage or beyond on our rocket, and we'd use a different engine to make it go higher.
We could also modify our topic. We could look at more modern rockets, like the Falcon 9 made by SpaceX. They have a rocket that has no fins and uses thrusters instead to calculate or to adjust its direction. We can make changes in the body, so we change the lengths of the tube and make them different proportions to the fins. And we could also make our rockets out of different materials, like different types of wood, plastics, and metals.
Any questions?
So how many launches did you make in total?
We had 15 combinations, but some of them failed, so it's probably around 18 to 20.
Okay.
Do you think the server that you attach to each rocket could have any effect on the value collection?
Possibly could, but we tried to make them as close to perfect as we could. So.
I think the surface of the materials you use, the immediate surface of the fins of the body of the nose cone have any impact? Like would you want it shiny versus rough or versus unpainted versus?
I think that did have an impact because, like, we think that one of the reasons the elliptical nose cone performed the best was because it was pre-made and it was plastic, so that could have seriously affected our data.
Any other questions?